Hi friends, see today we'll be starting the continuation with the Polycet examination 2025, that is second chapter in 10th standard new syllabus, that is magnetic effects of current. Okay, that is magnetic effects of current. In before videos we discussed about the chapter current electricity in two videos, part 1 and part 2. First concept we discussed and then numerical problems, around 19 to 20 problems we have done. Now please make a note, the second chapter magnetic effects. Already I told you total Polycet 40 marks in physics, 4 chapters, each chapter 10 marks you will be getting. But in this chapter maximum there is no numericals magnetic effects, only theoretical points are there. Maximum I will try to give some questions from this because there is no numericals from this one, only theoretical points. So maximum I will try to cover from 9 to 10 or 12 questions, theoretical questions in this chapter after completion of the synopsis. So let us start the synopsis of the magnetic effects. So actually this chapter in before days, many years back, that is up to 1819 to 1820. So in before days, this chapter was, electricity and magnetism were different concepts in physics. Electricity, magnetism were different concepts. But before the entry of a scientist called as Ørsted, that is Hans Christian Ørsted, a scientist called as Hans Christian Ørsted, great scientist, Hans Christian Ørsted. So he was explaining in the classroom with a simple circuit, a battery followed by a plug key and some bulb. Okay. So when he is explaining a simple circuit regarding a bulb, tap key and a battery to the students in 1819 to 1820, in that year, around that means 1820 year. Suddenly what happened, a magnetic compass kept beneath this one was deflected. Suddenly a magnetic compass kept beneath this circuit was deflected. Suddenly then he got a thought in his mind. Why this compass was deflected? Because I am explaining a circuit where current is passing in this one. Then finally he went into the laboratory and he gave some conclusions. Number 1, that is Hans Christian Ørsted. He has gave some conclusions. What are those conclusions means? First one, he thought in his mind, electricity at rest will have only electric charges. Okay, so that was the first thing got in his mind by the Christian Ørsted in 1820 from this experiment. It was accidentally discovered actually. Okay, that means electricity at rest will have only electric charges, only electric fields. And second point, electricity in motion electricity in motion means the flow of charges in any conductor, metal conductors like copper, okay, steel, like that. So electricity in motion will have both magnetic and electric fields. So this was the second conclusion given by Ørsted, Christian Ørsted in 1820 after this accidental discovery. Okay. First one is electricity at rest will have only electric charges. Electricity in motion will have both magnetic and electric fields. And third one is given is the directions of magnetic and electric fields, field lines, in other words. The directions of the magnetic and electric fields were given by the following rules. Those rules we'll be discussing now. Okay, by the following rules. Clear, all of you? So these are the main things given by the Ørsted scientist. Please draw the figure. Because first only I told you this chapter is completely theoretical chapter, magnetic effects. So after completion of the theory, I'll give some questions. Okay. So these are the main 3 points given by the scientist in his laboratory. Now let us go to the next continuation of this subject. How to find the directions, okay, magnetic fields, etc., etc. Okay. Now according to your syllabus, that is 10th standard syllabus, we have very less actually. When you go to 11th and 12th again, you will be having more regarding oil-state experiments and other things. So according to our syllabus is very less. So we will discuss what are the rules and regulations. First point, we have one rule, namely, that is Ampere's right hand thumb rule or grip rule. According to our syllabus, we have the first one, Ampere's right hand thumb rule or grip rule. So this is given by the scientist Ampere. Now according to this one, how to find the direction? For example, assume this is a conductor carrying current PQ. This is the direction, and I'll change the direction also another way. PQ, this is one direction. This is the direction of current, and this is the direction of current, other direction. Now what he is saying is from the rule. For example, this is your right hand. This is your right hand. Now what he is saying is right hand thumb rule. See here. Okay. Catch hold of the conductor carrying current in such a fashion that thumb indicates the direction of current. Thumb indicates the direction of current, and remaining curling fingers which are there, those indicates the magnetic field direction, it seems, according to rule. You can see these are the magnetic field directions. Circular. Okay. So if you observe carefully, you can see these fingers are coming outside. You can see outside. So in physics generally we use some rules. Inside we will be using this one. Outside we will be using, this is the symbol for outside. Magnetic field. Magnetic field direction. In general physics we will be using these rules. Into means into the board, into the page or board. Okay. If you put a dot means it is outside the board or page, outside. Magnetic field outside the page or board. So these are the symbols you will be using. Maybe you may be not knowing now, but in higher classes you will be using these symbols. Into means into the page, dot means outside the page. If you observe carefully here, thumb is indicating the direction of current, fingers are coming outside. So here the magnetic field is outside now, like this it is coming. In this fashion. Okay? Magnetic field in this direction you can see. Okay? So it is coming outside. So like this we can find out the direction of the magnetic field by using the following rules. Now coming back to here, if you observe, see, same right hand thumb. Okay? Now you can see fingers are going inside, you can see. See, this is the direction, fingers are going inside. So in this case it is magnetic field is inside. Okay, you can see here it is coming outside, here you can see it is going inside. Okay, so you can even draw in circular form and you can show also. These are the direction of the magnetic field. See here. So here it is going inside, like this, in this direction. Okay. So this is the direction of magnetic field, going inside. So put your thumb in this fashion along the direction of current, you can see fingers are inside. Inside means you can see magnetic field going inside and coming outside. Going inside and coming outside. Going inside and coming outside. Okay. But here it is coming outside, you can see the arrow marks. Coming outside. Okay. So like this you can find the direction of magnetic field by using Ampere's right hand grip rule or thumb rule. Clear all of you? Right. Now let us go to the next one. after learning about the ampere, sight and grip rule or thumb rule. So we are going according to your syllabus only, please. According to the new syllabus. Now, after knowing about ampere's right hand rule or grip rule, now what we will do is, we will explain magnetic field, what is magnetic field and what are magnetic field lines. Now, generally we all know about bar magnet. So this is a bar magnet, north pole, south pole. You can see this is a bar magnet, north pole, south pole. And we will try to draw some magnetic field lines. See how you will draw when you put a bar magnet here. Take a small compass. Try to put here. It will be deflecting because north and you will know the properties. See, we know some properties of magnets. See here, properties of magnetic. Okay, properties of magnetic particles. Or in other words, we can say the main properties. See, for example, north and north are there, north and south are there, south and south. These are the poles of the given magnet. And this is the length of the magnet. Generally the poles are little nearer and length is little more. Magnetic length is more than geometric length is more than the magnetic length. Okay. Now what are the main properties of the poles? You can say properties of the poles of the magnet. Main poles is, see here, north pole and north pole, same poles. In other words, it may be south or north, same poles. It may be north and north or south and south. Same poles will repel each other. Very, very important. We repel each other. It may be north and north or south and south. Repel each other. Okay? Repel each other. And next one, opposite poles. That means unlike poles, north south or south north. So unlike poles, here like poles, unlike, attract each other. Attract each other. So these are very, very important points you have to note down in your mind. And not only that one, a freely suspended magnet, you can always shows the direction along the geographical north pole of the earth. When a magnet is bar magnet suspended freely in the air, its north pole is always rotated toward the geographical north pole of the earth. Okay? So that indicates the north pole mainly. So these properties are very, very important for you in future. Like poles will repel, unlike poles will attract. Now, considering these basic concepts, we will try to draw magnetic lines. Considering these things, we will try to draw magnetic lines. For example, see, just now I told you, see, always from the north pole, the magnetic field lines will go and end with south pole. You can see anywhere. Always from the north, it goes and ends with south. Okay? It goes from north. Always it goes from north. Okay? The lines will go from north. It goes from north, ends with south. Goes from north, ends with south. These are the magnetic field lines, please. These are magnetic field lines. And these are very, very important. Changes when the north direction. Suppose in this case, if north is here, so the line will be like this. It is coming toward the south. See here? Coming toward the south. Okay? It is going like this, in this fashion. And here it is coming toward the south. So like this, you can explain the magnetic field lines for the bar magnet. Clear? And here also you have to make one point. The lines, magnetic lines. And first of all, you know what is magnetic field? What is magnetic field? The region or space around the magnet where its influence is felt is called as magnetic field. The region or space around the magnet where its influence is felt, that is called as magnetic field. And not only that, if you observe the magnetic field lines, the lines are very clear and distinct. the lines are very clear and distinct. You can see very clear lines. And second one, no two lines will meet each other. You can see no two lines will overlap, because if they overlap, the resultant will be in two different directions. That you will be studying in higher classes, 11th and 12th, by using vectors. So that is why, because that problem is there, no two lines will intersect. The lines are very clear. Okay, clear and distinct, and no two lines are very clear, will be meeting each other. If they meet, the resultant will be in two directions. Okay, and last one, if you draw tangent at any point, you will get the direction of magnetic field. If you draw tangent at any point, you will get the direction of the magnetic field. If you have tangent at any point, you will get the direction of the magnetic field. Direction of magnetic field. So these are the other important points regarding magnetic field lines, and these are done in the laboratory by using a small magnetic compass. Okay, so at beginning only I told you, little boring chapter, but still you have to study, because averagely from each chapter you are getting 10 marks. From each chapter you will be getting around 10 marks. So this is how the magnetic field lines are represented. Next one, still further we will be going. This may be a very small chapter, of course. Next one, magnetic field due to a current carrying conductor. Okay, another important thing I want to discuss before you is, from Oersted experiments, magnetic field due to a current carrying conductor. Now what is the main meaning of this is, suppose if you take any conductor, for example this is a conductor, say the current is carrying like this. Now what is the meaning of this one is, any conductor which is carrying current, it also acts as a magnet. It also acts as a magnet, isn't it? Why? Because when it is carrying current, use your thumb rule. Use your thumb rule. You can see, thumb indicates the direction of current, and remaining fingers, what happens? You can see, this is the magnetic field around the conductor. See here? So here you can see the fingers are coming outside. So field direction is outside. Field direction you can see outside, according to thumb rule. So current carrying conductor is nothing but what? It acts as a magnet. Of course it acts as a magnet. See? It is the field is coming outside. That means north pole is inside the board. Coming outside. North to south. That means south pole is inside. See, already just now I told you, if you take a bar magnet, north pole and south pole, how the lines are coming? North to south. North to south pole. See, north to south. North to south. So when the line is coming in this fashion, means north pole is inside. See here, you can see. Line is coming that side, means north pole is inside the board. South pole is outside like this. So like that it acts as a magnet, current carrying conductor or coil. Okay? Right. Next one. Already I shown you the diagram of the lines of forces, north and south. Next one, magnetic field through a straight conductor, that also we'll discuss. Next one, magnetic field due to a straight conductor. Magnetic field due to a straight. For example, this is straight conductor PQ. Suppose this is a current passing I. This is another conductor, same PQ. Let me I change the direction of current I like this. Now, we can do this experiment like this also. Suppose the current is passing like this. Again you can apply your right hand thumb rule, grip rule. See here? Magnetic field due to a straight conductor. That conductor may be long, that means infinity, or finite conductor. Now apply your thumb rule. Thumb indicates the direction. You can see the fingers are going inside. Fingers are going inside. So this is the magnetic field here. So this is magnetic field indicated with a B or bar because a vector quantity. Okay. So in this case, what happens? Field is in this direction. You can see. You can see yes. Field is in direction like this, going inside. Let me like this in this fashion. Okay, like this you can see, going inside. If you want, you can show it in circular way or with just like this you can show. Thumb indicates direction of current and fingers are going inside. That means magnetic field is going inside, coming like this. Okay, so in this case the magnetic field inside, coming like this. Now coming to here, second one. Here the direction of current is in this direction, you can see now. Okay, you can see. So here what happens? Outside it is, you can see. See here it is inside. Okay, and what about here? Fingers are coming outside. So here outside, magnetic field. So like that you can find the direction of the magnetic field as said before. Magnetic field due to a straight carrying conductor. So that when the direction in this fashion, the field is inside, and if it is in this direction, field is outside. You can see field is outside. Here inside, and here outside. It is coming outside, magnetic field. Like that, you can also, if you want, you can draw circle also. You can show by circles. Okay, you can see here. It's coming outside like this. Field is coming like this. That means it is coming like this. Like this. Okay, see here. Coming outside like this. So in this fashion you can find the direction, you can see. Coming outside like this, coming outside, going inside, outside, going inside, outside, going inside. See here? Here going inside and coming outside. Okay? So in this way you can find the direction of the magnetic fields by using right hand grip rule or thumb rule of ampere. Clear? Right? So these are some experiments, very very important. And we have one more also for easy method to explain. We have one more. Apart from right hand thumb rule, even though it is not there for you in syllabus also I am telling, sometimes we can use right hand curl rule also. It is also very much helpful. Sometimes to find the direction of current, we will be using right hand curl rule. For example, I will tell you, for this is a circular coil. For example, this is a circular coil. Current is going in this direction. This is another circular coil. Okay. This is another circular coil. Now here you can see the current is in this direction here. So this is clockwise direction and this is anti-clockwise direction. Now in these cases you can apply right hand curl rule also. Right? What is right hand curl rule? That means these four fingers curl along the direction of current. Curl along the direction of current. Then you can observe the thumb is going inside. Thumb is going inside. That means for in this case the magnetic field into the board. In the same way you can see the current is in anti-clockwise. Again use the right hand thumb rule and curl the fingers along the direction of current. You can see the thumb is indicating along the camera. This is the offside. You can see the thumb is coming this direction. That means magnetic field is outside. So like this also you can apply the right hand curl rule and you can find the direction of magnetic field. Curl the fingers along the direction of current. You can see thumb indicates into the board. Curl the fingers along the direction of current. Thumb is going outside. So here outside magnetic field, here inside. So in this case also you can find the direction of current. Little it may be advanced, but you can apply this one find the direction of magnetic fields. Next one, another two rules we have very important. These rules you can apply in the current carrying coil. For example, you have a magnets like this. For example, these are the magnets, north and south, and you know this is direction of magnetic field. The same way, now I'll change the direction. Okay, these are magnets. Now north pole is this side, south pole is this side. Now direction is this fashion, field direction, magnetic field. Okay. Now suppose in this, if you suspend a coil, which is carrying current, okay, you can see current is coming in this direction of the current. Okay, here also I am suspending one coil using a suspension thread. Now here you can see the direction of current. This is the direction of current. In such cases, what you will do is we will be using Fleming's. We will be using Fleming's left hand rule, which is also famously called as FLR. The same way, Fleming's right hand rule. Fleming's right hand rule, which is also called as FRR. Fleming's left hand rule, Fleming's right hand rule. Very easy. The scientist has given the rules to find the direction of the current, magnetic field and magnetic force when a coil is suspended in the magnets, strongly suspended magnets. And these are also used in the what you call as circuits, current circuits like generators, electric motors, please. These are also mainly used in electrical motors and also generators, electrical generators. So especially in these cases you can find the direction of current and direction of magnetic field and also magnetic force. Let me tell you first of all left hand rule. See your left hand, stretch your left hand 3 fingers, forefinger, middle finger, thumb finger. You can see here, forefinger, middle finger and thumb finger. This is forefinger, this is middle finger and this is thumb finger. Now these 3 are perpendicular to each other. In this way you can find the forefinger indicates the direction of magnetic field, the middle finger indicates the direction of current or velocity, and the thumb finger indicates the magnetic force. Are you following? So according to Fleming's left hand rule, you can find the direction. You can see. Suppose if you put north pole is here, south pole is, so magnetic field direction you can put like this. This is magnetic field and this is the direction of current and this is the direction of force. In this case, magnetic force is outside, you can see like this. Okay, so like that you can see this is the direction of current or velocity. In the same way, when the poles are reversed, here you will be using right hand rule. You can see right hand rule states that, see here, stretch your right 3 fingers of your right hand in such a fashion, middle finger, forefinger and thumb finger, 3 of them perpendicular to each other. Now what happens here? Middle finger again one side indicates the direction of current or velocity. This finger you can see here. Now the magnetic field direction, this direction, north to south. So this is the magnetic field direction and this is magnetic force direction. So in this fashion you will be using Fleming's left hand rule and right hand rule depending upon the polarity of the magnet. If poles are like this, north to south, use left hand rule. If poles are in this fashion, use right hand rule, and thereby you can find the direction of current or velocity magnetic force and magnetic field direction. Clear? So you can apply these in any circuits to find the exact direction of the current, please. Clear? Clear? Right. Please note down. Now, let us go to the next one. See, after knowing all these rules and regulations, let us go to solenoid. What is solenoid? Another important thing, solenoid. See, solenoid means nothing but a rectangular like structure, cylindrical like structure. On this, a copper wire is wound in this fashion. Okay, so current will be carrying here. And for example, this is north. Already I told you a current carrying coil behaves as a magnet before. So from north pole you can see the current lines will be going. The field lines you can see north to south, north to south. Okay, just it behaves like a magnet. I told you before. Any current carrying coil behaves like a magnet. Okay, clear? So this is the main function of the solenoid. Okay, it's a cylindrical like structure on which copper wire is wound. When the current is passing, it behaves like a magnet, just like you can see, like a bar magnet. So these are the lines of forces on the solenoid. Clear? So this is how you can explain the concept here, the magnetic field lines and other things on a solenoid. Clear? Please note down. As I told you, this chapter is little boring chapter, but still we have in the examinations averagely 10 bits are coming from every chapter out of 4 chapters. Each chapter averagely 10 questions. Next one, force acting on a current carrying conductor. Okay, force acting on a current carrying conductor. I think this will be the last one, second last one. Force acting on a current carrying conductor. See, already I told you just now. For example, these are the poles, magnetic poles. Suppose north pole, south pole. Now suppose this is a coil suspended here with a suspension thread. Now due to this one you have a magnetic field. Okay, you can see. Use your left hand rule. North to south direction, magnetic field direction. So forefinger magnetic field. Middle finger you can see the direction of current. Middle finger direction of current or velocity. And you can see the thumb finger indicates magnetic force. So this will be the magnetic force acting on the conductor carrying current. Conductor carrying current. Like this you can find the direction of magnetic force, please. So here specially you can apply Fleming's left hand rule or right hand rule depending upon the polarity of the magnet. Which side the north pole and which side the south pole. So like this you can find one will be upside, another will be down. Because if you apply here it is upside. And if you apply here it will be inside. So like that you can find the direction of the force. Okay, clear? So in this way you can find the direction of the things. Now last one to end up this chapter, that is domestic electric circuits, please. Please copy it. Domestic electric circuits. Domestic electric circuits. After this we will discuss the questions regarding examinations. Domestic electric circuits. As I told you, this chapter is theoretical chapter, no numericals in this one. Domestic electric. See, here we have to discuss some important points in domestic, that means in household. See, in household, you know, the current correction will be there. Main will be there inside main. 250 to 260 volts will be coming in the household for the domestic purpose. And we will be having lot of electrical appliances and connections inside our house, followed by refrigerator, AC, TVs and other things will be having, Android TVs. But here one thing you have to make a thing while giving connections wires inside the domestic purpose. You have to properly maintain the circuits. That means regarding the sockets and other things. Overloading should be avoided. That means sometimes what happens, due to improper connections of the electrical circuits, overloading will maybe acting on the wires. That means overloading, what happens? Sometimes the fuse may be going away. Okay, so to avoid that one, the technicians will be using fuse wire in the mains. Okay, fuse wire in the mains. Or sometimes latest technology MCBs are coming now, MCBs. Okay, you can see in every house nowadays you are having a lot of MCBs in the main, and each room will be connected with one MCBs, so that if anything happens, then MCB will be going upside. If any short circuit is coming or more load is coming, okay, it will be going up. So that is nothing but one way of protection for the electrical circuits. In before days it was not there, that MCB. So nowadays latest technology that is coming here. So for every room, for every single room, a connection is there. If any over current is coming, overloading, that will be going upside. Indication that you have to take care. Okay. So these are the things you have to take in mind while doing the connections. Okay. So generally what we'll do is, another important point I am going to tell you, that is earthing wire. Okay. So earthing wire is also mainly important here. If any excess of electrons are coming, it will be going into the earthing. So every house is also earthed properly, otherwise you will be getting shocks. Okay. And another thing you can see, we will be using a lot of electrical appliances in our household. So those electrical appliances will be protected by doing this earthing, please. Okay. So why we will be using, some questions are there in this chapter. Why we will be using fuse wires? Mainly to prevent the electrical appliances. What all electrical appliances will be using in our household, like mixies, okay, refrigerator, or Android TVs, washing machine, all these are very much generally used electrical appliances. So to prevent these things, in order to not to spoil, fuse wires are used to protect them. Okay. And not only thing, you have to take care regarding the sockets. So too many electrical appliances should not be kept in one socket. That also causes the overloading. So you have to reduce those things. Okay. So these are the main things you have to put in your mind for overloading and etc. Okay. Right. So I think I told you in the beginning only, magnetic effects of current is a very small chapter, and completely it's a boring chapter also, because completely theory, no numericals are there. Okay. So now this is the end of the chapter now. Now we'll be discussing the questions in the Polycet 2025 after the concept now. Okay. So now let us go to the questions in this chapter. What are the main questions asked in the Polycet examinations? Okay, let us go. First question. So first question from this chapter, magnetic effects, is magnetics effects of current. First one, for a magnetic needle or a magnetic compass, for a magnetic needle or magnetic compass, okay, the thing is, if you take any magnetic compass, so it is having north and south pole. So when it is brought near a magnet, it will be deflecting. Okay, it will be deflecting. So the question goes like this. Okay. First question you can take it like this. First one. Like poles will dash. Like poles will dash. A, B, C, D. Like pole means it may be north, north, south, south. Attract, repel, C answer both A and B. D none. So already I told in the concept, like poles, what happens north and north? They will be repelling. So A is B is the answer. B is the answer. Okay? Same poles, north and north, south and south, they repel each other. It's a nature's phenomenon. So B is the answer for the first question. Second one, unlike poles will be dash each other. Will be dash each other. A attract, B repel, C A and B, D none. So unlike means what? North and south, it may be south and north. So always in nature what happens, unlike poles will be attracting. So A is the answer, not A and B. Okay, it will be attracting. Clear? Third question. Third question, important question. Okay. Next question. So he may ask the question like this: overloading occurs due to dash. Overloading occurs due to dash. So here I am giving answers also for you. Overloading occurs due to dash. A, B, C, D. Okay. First one, live wire and neutral wire comes in contact. Okay, live wire and neutral wire comes in contact. A. B. Neutral wire. C. A and B. D none. So here the question, for this question, the choice is given in this fashion. Overloading occurs due to dash. Okay, in what condition overloading? Overloading means overcurrent occurs. What happens? I mean, what condition happens? Is this due to neutral wire or live wire directly comes in contact with neutral wire, or A and B, D none? So already just now I told you the concept. When a live wire directly comes in contact with the neutral wire, overloading. So A is the answer. A is the answer. Clear? Now next one. I told you this chapter doesn't have any numericals. You maybe have not having interest, but still the theory questions you have to discuss. Okay? Right. Next one. So this is the answer. When live wire directly comes in contact with the neutral wire. Okay now? Yes. Next one. Right. Next question, please. I think it's the fourth one. What is Fleming's left-hand rule? What is FLR? Okay? What is FLR? Fleming's left-hand rule. Okay? So where it is generally used? Fleming's left-hand rule. I told you just now, Fleming's left-hand rule is generally used in electric motors and generators to find the direction of the currents, please. To find the direction of currents. Okay? In what way the direction of current, magnetic field and magnetic force is going on. Okay, you can fill the blank here to find the direction of current or velocity, magnetic force direction and magnetic field direction. Fleming's left hand rule. Okay, that is the fourth question. Fifth one, what is Ampere's right hand grip rule? Ampere's right hand grip rule. Fifth question, what is Ampere's right hand grip rule? I told you this also in the concept. According to this grip rule, we can find the direction of what? Magnetic field. We can find the direction of magnetic field. That is the answer. We can find the direction of magnetic field, whether it is going inside the board or outside the board. This is mainly used by using Ampere's right hand grip rule. You can find the direction of magnetic field either inside or outside. I told you in the beginning. Next one. Sixth question. A current carrying coil behaves as a dash. I told you this also in the concept. A current carrying coil, it may be rectangular or circular. It is carrying some current. So it behaves as what? Dash. So answer is behaves as a magnet. Okay. So a current carrying coil behaves as what? Magnet. Just now I told you, when current is flowing, magnetic field direction is applied. That means by using the following rules, either left hand rule or right hand grip rule and other rules. So simply it behaves like a magnet. Seventh question. What is Fleming's right hand rule? What is Fleming's right hand rule? This also discussed. Fleming's right hand rule states that what happens? You can see, stretch your right hand in such a way that three fingers, middle finger, forefinger and thumb finger. So forefinger indicates the direction of magnetic field, middle finger direction of current or velocity, thumb finger indicates the direction of magnetic force. And these are already, I told you, it is used in generators and electric motors to find the directions. So this is Fleming's right hand rule. Clear? Right? Now, next question, eighth one. Magnetic lines. Eighth question. Magnetic lines always starts from dash and ends at dash. If you want, I am giving choice also. A, B, C, D. Magnetic field lines always starts from dash and ends at dash. South, north, north, south, A and B, D, none. So here the question is, magnetic lines of force always start from dash. I told you in the concept, it always starts from north and it ends to the south externally. Externally, always it starts from north and ends with south. So here the answer is B. Always starts, first dash is north, second one is not this one, not from south. Okay. Next one, ninth question. Very, very important. I told you this is a completely concept based subject, magnetic effects. Ninth one. Okay. Ninth question, coming to the same thing again. Right. Next one, I'll give regarding the rules of the magnets. I'll give regarding the rules of the magnets. See, already we discussed the points regarding the rules and regulations of the magnetic field lines. Okay, the rules and regulations of the magnetic field lines. Next one is no two lines. No two lines means magnetic lines. No two lines will meet each other. Will meet each other. See, this is another interesting question. No two lines, that means magnetic lines, will meet each other. A, B, C, D. So what the statement is, whatever the statement is given, no two lines will meet each other statement. He is asking you whether it is true or false. True or false. Okay? False, true, A and B, D, none. So what is the answer for this one? No two magnetic lines will meet each other. I told you the concept. If they meet each other, the resultant will be in two directions, which cannot be again found out. It is difficult. Therefore, what statement is given? No two lines will meet each other means if the statement is true, it is not false. Okay? So answer is B. The answer is B. So no two magnetic lines of force will be meeting each other. If they meet each other, the resultant will be in other directions. Two directions. So no two lines will meet each other. It is a statement true. Next one, 10th one. The direction of magnetic field can be found by drawing a tangent to the magnetic field is dash. That means true or false. The question is, the direction of magnetic field can be found by drawing tangent. This is also I told you the concept. How to find the direction of magnetic field? He is saying that, he is asking you, the direction of magnetic field can be found by drawing a tangent to the magnetic field. Is it true or false? A. True. B. False. C. A and B. D. None. So as I told you from the concept, to find the directions, always you have to draw the tangent at that point. And that tangent indicates the direction of the magnetic field in that direction. So the direction of magnetic field can be found by drawing a tangent to that magnetic field. Is a statement correct statement? True. So A. Clear? So these are the main questions in your magnetic effects. As I told you, this chapter is very small chapter and concept based chapter it is. So main questions I have discussed, hardly I got 10 questions regarding the examination point of view. And in current electricity we have discussed lot of questions because it's actually problematic. So nearly I have discussed 19 to 20 questions, 19 to 20 numericals after the concept. But here we have very few questions. Hardly we are getting 10 questions in this chapter. So please prepare well for these questions in this chapter. Completely a theoretical chapter. So sometimes he may ask 10 or he may ask less also. Total 40 questions are there in the Polycet examination. Okay. So prepare well. Again we will be meeting in the next chapter.